So in this video we're going to talk a little bit about the derivatives of trigonometric functions. We started to talk about this in class on Monday, but I just wanted to continue that conversation and lay out the new rules that we're going to use here. So to start off, we need to make sure that we remember what the graphs of y equals sine of x and y equals cosine of x look like. Hopefully you do recognize that this graph on the left is the cosine function. If we look at these key data points here, they represent the typical cosine behavior. We start at one unit above the origin and then we drop down and so on. And so if we were talking about this being the cosine of x function, then its derivative, I'll use a different color here, let's try to figure out what function that is. Well, as it turns out here, the slope at this particular data point is 0, so I'm going to put a dot here at 0 on the y-axis. The slope here is negative, and as it turns out, it is precisely -1. This slope is 0, so we'll put a dot here at 0. Now we've got a slope of +1, and then again a slope of 0, and so on, and this pattern continues. And the data points, if we were to connect them on this derivative estimation, well, this ends up looking like a trig function as well. Let's see if I can kind of recreate that here. So this is a trig function as well, and this function looks more like a sine function in that it starts at 0, but remember on a sine function we typically rise from the origin instead of falling from the origin. So as it turns out, for the function cosine of x, its derivative is the opposite of sine of x. And we can add that to our derivative rule list. Now again, we're not trying to prove these to be true. We're not establishing them using the limit definition, but anecdotally and observationally, I suppose, I think this tends to make a little bit of sense. The derivative of cosine appears to be negative sine. Now in this function over here, we'll use the same approach. This time you might recognize that this function is sine of x. So again, we're starting at the origin, and as we increase our angle measure, essentially, pi over 2, we have a function result of 1, and then pi, we have a function result of 0, and so on. So these data points do represent the points on a sine curve. So what's the derivative here? Is it going to be negative cosine? If you're making an estimated guess, that seems reasonable. The derivative of cosine was negative sine, so let's see what the derivative of sine is. Well, the slope at this particular data point is positive, and it is actually +1. That's a precise slope there. We can show that to you at another time. So I'm going to put a dot here. That's y equals 1. Then at this position, we have a slope of 0, so I'm going to put a dot here at 0 on the y-axis. Here we've got a negative slope, so I've got to be down below the x-axis, and it happens to be -1. And then a slope of 0, slope of +1, and so on. So we've got some data points here that can be connected, and these data points, when connected, represent a function that is the derivative of cosine. I'm sorry, the derivative of sine. So if this is the derivative of sine, what shape does this red graph look like? Well, hopefully you recognize it, that this graph is actually the original cosine function. So the derivative of sine is not the opposite of cosine, as you may have guessed initially, but it's actually just cosine itself. So those are two more of our trig rules that we're going to use while moving forward. Now let's take a look at one more. Hopefully you recognize that this graph is our tangent graph. And let's see if we can figure out the derivatives of these tangent arms or tangent legs. I'm just going to look at a couple data points here on this graph. At this spot in the tangent function, we actually have a positive slope, and I think, if I'm not mistaken, that slope is precisely 1. So I'm just going to put a dot here at 1 on the y-axis. Now if I look a little bit further to the right, you can see that the steepness of the graph right here is actually increasing a little bit and increasing more and more and more. So if we consider these data points as we move further and further to the right, the function is becoming more and more steep in the positive direction. And it almost looks like, because of the tail of this tangent branch, it almost appears that the slope is getting infinitely large. and that's exactly what's happening. So I'm going to draw this curve kind of like this, where it's increasing and becoming infinitely large as we move to the right. If we try to reach an x value of pi over 2, the tangent function in red is undefined at that position, and the slope therefore would be undefined as well. So I don't want to let this arm, I don't want it to cross the vertical line at pi over 2, but I do want it to approach that. So there is an asymptote here in the derivative graph, just like there's an asymptote in the function graph as well. But I do want to show that it does get steeper and steeper as we approach it. Now what if we start looking at positions to the left of where we started? Well, we see the same sort of thing. We see the really steep looking graph as we look to the left. And there may be a tendency to think that these slopes are negative, but remember, we always read slopes and we tend to read graphs from left to right. So if I look at any one of these positions along the way, they actually also have a positive slope. The value of the function is decreasing, but the slope is very much positive. It's very steep over here on the left, and it becomes a little bit less steep as we approach the right, but in any event, we have a collection of positive slopes the entire time. And so if I were to sketch a picture of the slopes here, I might sketch it this way. Again, all of our slopes are positive. They just become more and more positive as we look further to the left. These are definitely the steepest slopes that we encounter on this branch of the trig function. Now, if that's the behavior of this particular function, we could look at every single branch and essentially recreate the same thing, because all of these branches of the trig function operate the exact same way. So what we have now is just a collection of these U-shapes that are pointing upward. And those two sketches aren't that great, but indicative nonetheless. And so the question now becomes, well, what's this function? What does this series of U-shapes represent? And some of you might recognize, well, this kind of looks like a secant graph or a cosecant graph. Those are the ones that generated these U-shapes, but in a secant and cosecant graph, we ended up having alternating U-shapes, so some that pointed up and then some that pointed down. So this isn't precisely a secant graph or a cosecant graph, but we can actually force all of our U-shapes to open up if we take a secant or cosecant graph and square it. That way any negative result from the secant computation becomes positive while being squared. It does change the numerical values just a little bit, and as it turns out here, the U-shaped curve that we see in each of these instances does indeed follow the secant function behavior, and secant squared is the derivative of tangent of x. Now the proof of this is a fair bit complicated, and I'm not going to bother to try going through it. In fact, I don't think I've ever worked through it personally myself, but it has been done, and we can take other mathematicians' word for it that this definition is indeed true. The derivative of tangent of x is secant squared of x. And when we're in class, we can talk about the differences between secant and cosecant again, if you've forgotten. So here are the 6 derivatives of trigonometric functions that I'd like for you to memorize. Sine, cosine, tangent, we've already talked about those 3. There are 3 other trig functions, cotangent, secant, and cosecant, and their derivatives are supplied as well. Now, the secant function and cosecant functions, their derivatives look to be a fair bit complicated, and we may see a couple examples of those in this class, but I do want you to memorize these in the event that we come across them in an example or two in this class. So again, add these please to your derivative list. Now just to round out this video, maybe we'll do a couple practice problems here. We have the function y equals sine of x plus cosine of x. I'm not really sure what that looks like, but in the event that I'm interested in the derivative, let's use this notation. Let's use dy dx. I was about to write y prime, which is acceptable, but I'm going to write it this way just so that we have the practice. Well, we have 2 distinct functions in this function y, and those functions are being added together. So of course our derivative rule stated that I can find the derivative of the first function and add it to the derivative of the second function. So the derivative of sine we just learned was cosine of x, and the derivative of cosine is negative sine of x. Now you might want to simplify this a little bit further, or you might take the chance of submitting that to Math Excel if this is a question that you see there. But more often than not, instead of adding a negative sine of x, we would write this as cosine of x minus sine x. So the derivative of y with respect to x is cosine of x minus sine of x. For this second example, we have two functions again. This time they're being multiplied together. So if you recall, when we learned our product rule, we said it's a good idea to consider what your first function is. So I'm going to call this one e to the negative x, and consider what your second function is, sine of x. That way you can compute the derivatives of each. So the derivative of e to the negative x, this is kind of like that rule number 12 or 13, I think, e to the kx power. K happens to be negative 1. So I'm going to write this as negative 1 e to the negative x power. That's our derivative of e to the negative x. And we just learned that the derivative of sine is cosine. So now when we find the derivative of y with respect to x, we take the derivative of the first function, multiply it by the second function, untouched. So we'll take negative e to the negative x, multiply that by sine of x, and then to that we add the product of the first function, untouched, times the derivative of the second function. So this one would be e to the negative x times cosine of x. Now with these functions that are pretty different from one another, e to the x and sine, or e to the x and cosine, I don't really see any way that we can simplify this. Certainly there is a common factor, e to the negative x, and you could factor that out. I'm not entirely sure that that's beneficial here though, but maybe you would think that it is. So if I factor out e to the negative x, which is common to these two terms, that leaves me with negative sine x plus cosine x, or better still, e to the negative x times cosine minus sine. So I think any one of those are acceptable. If it were me completing this on my own in Math Excel, I would probably try this answer first, see if they'll accept it, because it is correct. The others are just a factored form of that. But it doesn't appear to me that any of those are more simple than the other. So in the last example, we've got y equals x sine of x, and here again I recognize this as two functions. So I'm going to use the product rule, and this time I'm going to try to do so without writing down our first and second functions. This is a good idea to practice to make yourself better at using this rule. So we'll go with the derivative of the first function is 1 times the second function, so we've got 1 times sine of x, plus the first function times the derivative of the second. And there we go. Sine of x plus cosine, x times cosine of x. And there's no simplifying there, no common factors or anything, so I think that's good to go. We found the derivative function without much work at all. Now I do have a couple other examples at the bottom of this page for us to look at if you so choose. They are two examples of our quotient rule, and then also this cosine squared. We haven't learned about the chain rule just yet, but we can actually solve this one by considering this as cosine of x times cosine x. So while I'm done presenting in this video, I would suggest that you try these three examples on your own. You can pause the video now and resume playback in a moment to check your work. Now, this example actually became a bit more interesting than I originally thought. One thing I want to point out here is that with the quotient rule as well as the product rule, it is a good idea to write out your top and bottom functions, high function and low function as we called them in class, f and g, and then to calculate their derivatives. But one thing I wanted to point out here is that when you follow the structure of the quotient rule, the low function times the derivative of the high function minus the high function times the derivative of the low function, what I would recommend is that you just stop here for a moment and maybe put a box around this answer for two reasons. Number one, this is a way for me to check to see if you executed the quotient rule correctly. And then also, I think it's a good answer that Math Excel might accept. Now, what we can do from here, though, is simplify it further. And we can distribute across the numerator and combine like terms if we see any. But the denominator, and this is a good point to take here, the denominator we almost never distribute because there's almost never a time where the factors from the denominator will cancel with the numerator. But I'm going to take a moment and actually distribute across the numerator here and show you that result. Now, in and of itself, this doesn't look all that interesting, but maybe you notice that there's a -1 acting as a common factor in that numerator. I'm going to slide over here so that margin line's not in our way either. So I'm going to factor out that -1 in the numerator, and then I'm also going to reorganize that numerator just a little bit too. Now, the reason why I reorganized this way is that hopefully you recognize a trigonometric identity from last year. Sine squared of x plus cosine of squared of x does reduce to the value 1, so we can actually eliminate that, and now we're left with the opposite of sine of x divided by sine x plus 1 quantity squared. And this is where I would probably stop simplifying this expression. It's a fair bit different than what we produced in the very first step, but you'll notice that there was a lot of algebra used to simplify that, as well as some trig identities. So again, I like to see this answer here first so that I know that you applied the properties correctly. And then we'll talk about it as we get a little bit more practiced with our derivative rules, whether or not I'll expect to see this solution for our upcoming test. So I think that's a good stopping point here. I'm going to switch to another screen to show you my solutions for these other two examples, and you can check your work against them. Thanks for watching.